Somewhere out past the edge of everything we can see with the naked eye, two machines are drifting through absolute darkness right now, at this exact second. Everyone knows the first one. Voyager 1, the record breaker. The spacecraft with the golden record. The one that crossed into interstellar space back in 2012 and never stopped making headlines since. But almost nobody talks about the second machine. Its twin, Voyager 2, quieter, less famous, sampling a completely different region of interstellar space, moving in a completely different direction, 13 billion miles from home, carrying something Voyager 1 lost decades before it ever reached the true edge of our solar system. A working instrument, one that turned out to be the single most important tool for understanding the true boundary of our solar system, an instrument that no model built before its arrival had correctly predicted the readings of. And in the summer of 2026, that overlooked spacecraft is at the center of the riskiest procedure NASA has ever attempted on either Voyager machine. No backups, no second try. If it fails, we lose data nothing else on Earth can replace, possibly for the rest of this century. And whatever happens to Voyager 2 in the coming weeks will directly shape what NASA even dares to attempt on its more famous twin. So why does any of this matter to you, sitting here in 2026, decades after these machines launched? Because what Voyager 2 measured at the true edge of the solar system didn't just confirm what scientists thought they already knew. It broke their models. It found a boundary that leaks in both directions, a temperature reading that was off by half, and a structure nobody predicted, one that behaves less like a wall and more like a coastline. And right now, engineers are gambling the future of that spacecraft on a single all-or-nothing maneuver, nicknamed the Big Bang, that could either buy it years of extra life or end its mission in a single afternoon, 16 hours after the command is even sent. Whatever happens in the next few weeks will decide whether Voyager 1, since New Voyager 1 gets the same chance in July, and whether one of the last shutdown instruments on either spacecraft ever gets the opportunity to switch back on again. Rewind to August of 1977. Two nearly identical spacecraft left Earth just 16 days apart, launched from the same program, built by the same engineers, carrying nearly the same set of instruments. Voyager 1 lifted off second, but was placed on the faster route, aimed at Jupiter and then Saturn, where it would use Saturn's massive gravity to slingshot itself northward, out of the plane where the planets orbit, and head for interstellar space as quickly as possible. That path traded distant planets for speed, and for a closer look at Saturn's largest moon, Titan. Voyager 2 launched first, but took the long way. Mission planners gave it a far more ambitious trajectory, one that would let it visit not 2, but all 4 giant planets in our solar system, something no spacecraft before or since has managed to accomplish. That decision meant trading speed for scope. Voyager 2 wouldn't reach the true edge of the solar system nearly as quickly as its twin, because every additional planetary flyby meant another detour, another gravity assist, another few years added to the outbound journey. Voyager 1 crossed into interstellar space in August of 2012. Voyager 2 didn't get there until November 5th, 2018, more than 6 years later. For 6 full years, scientists studied Voyager 1's crossing as the only real data point they had for what the edge of the solar system actually looks like, building models and drawing conclusions from a single vantage point. Then, Voyager 2 arrived from an entirely different angle, and everything they thought they understood needed a second look. Both spacecraft still run on the same basic power source they launched with, small generators that convert the steady heat of decaying plutonium into electricity, chosen specifically because sunlight becomes far too weak to rely on once a spacecraft passes beyond the orbit of Mars. That single design decision from the 1970s is the entire reason that either machine is still capable of transmitting anything back to Earth nearly 50 years later. Here's the detail almost nobody brings up when people talk about Voyager 1's historic crossing. Its plasma instrument, the device built specifically to measure the temperature, density, and speed of charged particles both inside the solar system and out in interstellar space, had already stopped working long before the crossing happened. Not at the boundary, not even close to it. It failed back in 1980 before the spacecraft had even reached Jupiter's orbit on its way out of the solar system. That means when Voyager 1 finally crossed into interstellar space more than 3 decades later, it did so completely blind to the one measurement scientists needed most at that exact moment. Researchers could estimate what was happening using other onboard tools, the cosmic ray detector, the magnetometer, the plasma wave system, but they could never get a direct reading of the plasma itself on either side of the line. There was a hole in the data that had existed for 32 years by the time the crossing finally happened, and nothing on Voyager 1 could fill it. Voyager 2, on the other hand, still had a fully functioning plasma sensor when it made its own crossing in 2018, more than 4 decades after launch, in the harsh radiation environment of the outer solar system. For the first time in the history of spaceflight, scientists had a working plasma instrument physically present at the true boundary of the solar system, measuring particles on both sides of the line simultaneously as the spacecraft actually passed through it. That single working sensor produced what researchers later described as one of the most historically significant datasets in the history of planetary science, filling a gap that had sat empty since before most people alive today were born. Think about that timeline for a second. The instrument that finally answered the question had been quietly working, untouched by human hands, through 4 decades of deep space radiation, temperature swings, and mechanical wear, long after most of the engineers who built it had already retired. What that instrument found didn't line up with the models at all. Scientists had long assumed the boundary of the solar system, the point where the outward pressure of the solar wind gives way to interstellar material, would be sharp and thin, a narrow line only a few 100,000 miles wide. Instead, Voyager 2 detected a transition zone roughly 100 million miles across, sitting just outside the true edge, in territory that was supposed to be pure, untouched interstellar space. Streams of interstellar particles were pushing inward through that boundary like roots working their way through solid rock, blending with material from our own solar system far deeper than any existing model expected. And the 2 spacecraft, crossing at almost the same distance from the Sun but 6 years apart and from different directions, saw completely different versions of this transition zone, which told researchers the boundary isn't uniform at all. It shifts shape depending on where you happen to be standing when you cross it. One of the mission's senior scientists, the principal investigator on one of the low-energy particle instruments, put it bluntly when the findings came out. Nobody fully understands why the boundary sat at almost the identical distance from the Sun during both crossings, even though one happened during a period of high solar activity and the other during a much quieter stretch of the solar cycle. Existing models had predicted the size of this bubble surrounding our solar system should visibly expand and contract with the Sun's activity level. Both crossings showed it barely moved at all, a result the scientists described simply as something researchers do not yet understand. Coming from someone who had spent decades studying data from both spacecraft, that kind of plain admission carries real weight. It's not a minor footnote. It's a signal that something basic about the relationship between our Sun's activity and the size of the bubble it carves out of the galaxy does not behave the way generations of models assumed it would. The third finding is the one that the mission's longtime project scientist called the most remarkable of all: the boundary leaks. Not as a metaphor, literally. Scientists had always pictured the edge of the solar system as something close to a wall, a clean, defined separation between our neighborhood and the rest of the galaxy. What Voyager 2's data actually showed was closer to a coastline, with material washing across the border in both directions at once, the way surf runs, back and forth where 2 oceans meet. On its own approach, years earlier, Voyager 1 had already picked up hints of interstellar particles pushing their way inward through the boundary. Voyager 2, coming from an entirely different direction years later, detected the reverse effect, a steady trickle of solar particles leaking outward into interstellar space before the spacecraft had even finished crossing the line itself. 2 spacecraft, 2 separate crossings, years and directions apart, and both arrived at the same basic conclusion. Material moves across this boundary constantly, in both directions, all the time, and whatever mechanism causes, that leakage is a fundamental property of the boundary itself, rather than a local, one-off event. On top of that, the plasma readings revealed something scientists had only ever been able to estimate through theory before. Interstellar space beyond the boundary turned out to be more than 40 times denser than the solar wind measured just inside it. And its temperature, measured directly for the first time in the history of spaceflight, came out to somewhere between 30 and 50,000 degrees. Hot by ordinary standards, but dramatically cooler than the tens of millions of degrees recorded just inside the boundary, where the solar wind still carries the heat of its origin. The earlier theoretical estimate of that interstellar temperature had been wrong by roughly a factor of 2, a gap that direct measurement finally closed. As the mission's project scientist explained when the findings were announced, the 2 spacecraft weren't simply marking the point where the Sun's influence ends. They were revealing how our entire solar system actively and continuously interacts with the material that fills most of the space between stars across the galaxy. Every one of these findings came from published, peer-reviewed research, cross-checked by teams at NASA's Jet Propulsion Laboratory, and confirmed across 5 separate papers released together in a leading scientific journal in late 2019. This wasn't speculation, and it wasn't a single scientist's pet theory. It was the collective conclusion of an entire research community working with real, measured data from 2 independent spacecraft, arriving at the same boundary from opposite sides of the solar system, years apart, and still landing on the same unexpected picture. And notably, both spacecraft, even at more than 13 and 16 billion miles from the Sun, are still sampling a region that scientists consider disturbed and transitional rather than truly calm, untouched interstellar space. In other words, even now, neither Voyager has fully escaped the influence of the solar system it left behind so long ago. Step back from the specific numbers for a second, because the real story here is bigger than one spacecraft or one dataset. When mission planners designed the Voyager program back in the 1970s, using computing power weaker than what sits inside a modern pocket calculator, they deliberately built a two-spacecraft mission instead of relying on a single probe. The reasoning was simple. One data point can't tell you whether what you're seeing is typical or a fluke. Two spacecraft, launched on different paths, arriving at the boundary from different angles and at different points in the solar cycle, could start to build an actual picture instead of a single snapshot. What the original planners couldn't have predicted was that the instrument which would turn out to matter most for understanding that boundary would fail on one spacecraft and somehow keep working on the other for 4 more decades. The division of labor between the two Voyagers was planned. The specific way it played out, with one twin picking up exactly where the other twin's broken instrument left off decades earlier, was not. That's the kind of accidental symmetry that doesn't happen twice. And Voyager 2's list of achievements stretches far beyond the helipause crossing. It remains the only spacecraft in human history to have visited all 4 giant planets. At Uranus in January 1986, it discovered 10 previously unknown moons and 2 new rings. It measured a magnetic field so strangely offset from the planet's rotation that it still challenges scientists today. At Neptune in August 1989, its final planetary encounter, it discovered 6 new moons, clocked supersonic winds faster than anything else recorded in the solar system, and photographed active nitrogen geysers erupting from the surface of the moon Triton. It also returned the first close images of Europa's cracked, icy surface, images that eventually helped inspire an entire modern mission built to search that moon for signs of a hidden ocean. Earlier in its journey at Jupiter, it spotted a 14th previously unknown moon and confirmed the active volcanic eruptions on the moon Io that its twin had first detected only months before. At Saturn, its instruments revealed a level of structural complexity inside the planet's rings that ground-based telescopes had never been able to resolve. Almost none of this required a second mission or second launch. It all came from one spacecraft, built to last 4 years, still delivering new science more than a decade after most people assumed it had nothing left to give. This is also a reminder that humanity currently has no other way to directly sample interstellar space. No other instrument exists anywhere near where these 2 machines are right now, and none is expected for decades. Whatever data these 2 spacecraft can still gather before their power finally runs out may be the only first-hand interstellar measurements available to scientists for the rest of this century. Which brings us to right now, this summer in 2026. Voyager 2 currently has 3 working science instruments left. The plasma sensor that made the historic 2018 crossing measurements possible, the magnetometer, and the plasma wave system. Together, they're still delivering something no other piece of equipment in the history of astronomy has ever provided. A live, continuous, in-place reading of conditions in interstellar space from a machine that is physically located inside it, moving at roughly 34,000 miles an hour. But the power supply is running out, steadily and mathematically, with no way to reverse it. Both Voyager spacecraft rely on the slow decay of plutonium inside their generators, a process that costs each one about 4 watts of usable power every single year. At launch, each spacecraft had close to 470 watts available. Voyager 2 currently has a slightly larger power cushion remaining than its twin, which is why it still runs 3 instruments, while Voyager 1 dropped to 2 after one of its remaining instruments had to be shut down back in April of this year. That cushion is shrinking fast, which is exactly why engineers at the Jet Propulsion Laboratory built a plan nicknamed the Big Bang, an all-at-once reconfiguration of every remaining powered system on the spacecraft, switching some things off entirely and replacing others with lower power alternatives, executed as a single coordinated operation instead of gradually over time. The reasoning behind doing it all at once is about risk. Gradual changes leave the spacecraft sitting in unstable in-between states for longer. And those states can trigger automatic safety systems that begin shutting instruments down on their own the moment they detect power draw exceeding what the generators can supply. Doing everything simultaneously means spending as little time as possible in that dangerous middle ground. And every single command sent during this test has to travel more than 16 hours to reach the spacecraft, with every response taking another 16 hours to return to Earth. There is no room for a quick fix if something goes wrong mid-procedure. If this reconfiguration works cleanly on Voyager 2, engineers plan to attempt the identical maneuver on Voyager 1 no earlier than this July, with hopes that success there might even allow one of its already shut down instruments to be switched back on. Engineers chose to test the procedure on Voyager 2 first, not because its mission matters less, but for the opposite reason. It currently has a slightly larger safety margin, which makes it the safer place to try something that has genuinely never been attempted before at this distance from Earth, by a small and aging team working with spacecraft systems that predate most of their own careers. So what actually happens if this fails? Voyager 2 loses instruments faster than planned, and some of the last live measurements humanity has of interstellar space go dark years earlier than they otherwise would have. There's no backup mission waiting in the wings, no replacement spacecraft already built and sitting ready to launch toward the boundary of the solar system. Whatever gap opens up would stay open for decades, possibly much longer, until some future mission that hasn't even been designed yet, let alone funded or launched, eventually makes the same nearly 50-year journey these two machines already completed. And if it succeeds, Voyager 2 keeps transmitting real interstellar data for at least another year, quite possibly more, continuing to help scientists chase down the questions, its own boundary crossing, raised but never fully resolved. Why does the edge of the solar system sit at almost the same distance from the sun, regardless of how active the sun currently is? What actually shapes that boundary, if not the raw strength of the solar wind pushing outward? Is the entire heliosphere shaped like a long comet tail trailing behind the sun as it moves through the galaxy? Or is it closer to a sphere, or something else entirely that nobody has proposed yet? Every extra month these spacecraft manage to survive adds another real data point toward answering questions that, right now, genuinely nobody on Earth can answer with confidence. And beyond the specific numbers, there's a simpler reason to care. These two machines represent the only first-hand contact our species currently has with the space that lies beyond our own solar system. And once their power finally runs out, that contact ends for a very long time, regardless of how many other missions get funded elsewhere in the meantime. Think for a moment about what these two machines actually are. Two spacecraft roughly the size of small cars, built with wiring and circuitry from an era before the internet, before GPS, before anyone carried a computer in their pocket, designed by engineers who fully expected the entire mission to be finished within about 4 years. Instead, nearly 50 years later, they're still out there, still listening, still sending signals back across billions of miles of absolute darkness, still measuring a region of the universe that no human-built instrument had ever touched before they arrived to sample it directly. The people keeping them alive today are a small, aging team working out of a single building in California. Some of the last engineers on Earth who still understand these systems well enough to talk to these machines in the exact language they were originally built to understand decades ago. When that specific knowledge is gone, once the last person who holds it retires, it doesn't simply come back from documentation alone. Somewhere out past the edge of everything, two machines launched almost half a century ago are still whispering to Earth from the space between the stars. And for now, against every original prediction made about them, they are still being heard, faintly, 16 hours late, but heard. Every signal that arrives is proof that a decision made by a small group of engineers in the 1970s, working with computing power we would now consider a toy, is still paying off in ways nobody at the time could have fully guaranteed. The result of the Big Bang test in Voyager 2 is coming. What happens next for Voyager 1 in July is coming. If you want to know the moment either signal arrives, subscribe now, because the next transmission from 13 billion miles away could quietly change what we know about our own solar system all over again.